Hello, everyone. I'm Alan Willard, Senior Development Relations Technical Artist, and I'm going to be talking about particle stuff today. Mostly because that's what I've been doing lately, so it at least is something that I've had on my mind a lot. Um, so I'm going to do a mix of basics and some more advanced stuff. I'm going to talk a little bit about spawning particles from other particles and having them track that position and mixing GPU and CPU particles together and why we would do it like that. Without much further ado, we'll go ahead and get started. I've got a new project here. It's called just Alan More Particles. And I'm already in the material folder of the content browser or asset browser. And I'm going to create a particle material to use here. So, and particle mat. And what I'm going to do is I'm going to create a procedural dot, something that will hold up. It's not going to have any compression artifacts or anything like that. It'll just work. So the first thing we'll do is drop in a texture coordinate and a sphere mask. And if you've watched some of my other streams, we use sphere masks to give a radial fall off from a coordinate space. So in this case, the texture coordinate looks like this. It's a gradient going along the x and y axes, or x and y axes. And then we're going to find the midpoint, or 0.5, along both of those vectors. And that will give us something that looks a bit like this. So I now have an extremely crisp circle. I don't want it to be quite that crisp, so if I bring the hardness down to, say, 50%, you'll see it begins to get a little softer. At 0, it's a linear fall off from the center out, so the center would be a value of 1, and the outermost edge would go to 0. So we'll do about 20% because I want a little bit of a core to it, and then we're going to drop in particle color. We'll drive that directly into the emissive, so the red, green, and blue channels will drive the color of the particle, and the alpha channel we will multiply with our sphere mask. And this will give us the soft-edged dot that we're looking for the final particle. So we'll set the blend mode to translucent and the shading model to unlit, because we're not doing a lit particle in this case. Stop previewing the sphere mask, and we get our nice soft translucent dot. So this is especially for things like sparks and trails, little trailing dots that follow something. This is a pretty common way of accomplishing that. So now, jumping back to the asset browser, we will use or create a particle system, pfx underscore example 1. And we'll find that material that I created and particle mat, and we'll set that as the default material here. So once it compiles that, we'll see we get a nice soft blending dot. Now, of course, if I change properties, say the color over life, I'll get rid of the timeout here. At the end of the particle's lifetime, I'm only going to set the color once in this case. Dragging this value around, you'll see the particle system change. I still get the nice smooth fall off, but I'm now pushing it more towards blue or any other color I wanted. If I wanted more of a blue-green or just yellow, green, whatever, you can see all those colors change. So in this case, we're going to start off with a mostly white spot, shading just a little bit towards the red-orange side. So it's just slightly, almost a beige. And we're going to change some of the properties in this so that we get more of that spark look that we're going for. So we're going to change it so that the particle system faces its velocity. Now, because the particle is square, it's going to look pretty much the same. If I look straight down at it from above, you can see that it's a little different than it was before. If I set it back to square, you'll see with square, it will always face the camera. With velocity, it's trying to face both the camera and the direction that it's moving. So it's moving up, and then it's also spinning the particles along the other axes to follow me. So if I set the size to something that's not square, so here we've got x, y, and z are all 25. If I change this to a constant and say my x is 5 and my y is 10, I start getting that more stretched look, and as I increase the difference between these, that will get stronger. So now I've got something that's almost a little dash moving along that vector. So this, at its most basic, is how we do a lot of sprays of sparks. If you have a welding effect or something like that, I would add a little bit of acceleration, or sometimes a lot, depending on what I need. So say negative 600, and my initial velocity would be something like 250 along x with a little bit more along z, and say 100. So now my sparks are coming out in a single direction. If I reduce the amount of z there, or even go negative, I'll start getting kind of an outward push with a little bit of change in velocity. So this is the kind of behavior that we can do, some pretty simple effects that we can then compound on top of. So if I want to have something that has a little more behavior to it, I can do something like rename this emitter to source. I'm going to drop the spawn rate because I'm not going to want as many of them, because I'm going to fill it with something else. So now we have little spits coming out, and I'm going to create a new particle system. Now, because I had that particle material selected, it's going to show up using that material automatically. But in this case, we're going to change to GPU sprites, so we can have quite a few more of them. We'll go ahead and set the bounds. The bounds are the invisible box that determines whether or not this is in view. If the camera can see any portion of the bounds, you can see them like this. If it can see any portion of the bounds, it will render the particle system. So for GPU particle systems, we use a fixed bounding box because the GPU doesn't tell the rest of the engine how big the system is getting. All of that is handled on the GPU. So this lets us preset that. So I'll do positive and negative 500 for my range, and my bounds, which were kind of chaotic, will now be square. And you'll notice that the warning that I have a GPU particle system with no bounds has gone away. So now I can basically replicate a lot of the same behavior that was being set up in the CPU particle system. We're going to do velocity, not rectangle. We're going to do an initial size that is stretched along one particular vector. But we're going to kill the velocity, so they're just going to spawn in place, and we're going to choose a location emitter, or a location module that's called emitter initial location. And what this is doing is it's saying, when you spawn this particle, pick another particle's location as the new spawning location. And we determine that by the name. So my renaming the particle system before has now left these particles spawning where the other system was. So I'm going to increase the spawn rate dramatically, say 2000, and now we've got these trails that you see, almost arcs, but it's not inheriting any of that velocity yet. So we're going to inherit the source velocity, bring it down a bit, so now I've got streaks that are being created. Make sure my bounds are set correctly. Yeah. And now we're going to add some other behaviors like drag. So drag is going to slow down the particle systems as they move. It's acting like I didn't set the bounds correctly. I did. So you'll notice these particles are getting left behind, but the amount of drag combined with their velocity is going to slow them down over their lifetime. I'm going to change the color of my trailing particles a bit so that I can identify them versus my kind of core spark. So we'll make these strongly blue. So now my sparks are coming out and they're that kind of beige color. Now, to make these brighter, to get that spark look, one thing I could do is go into the color over life and begin dragging these values up really high. But what I found works pretty well is if you go into color and scale the color over life, normally this would be something that would allow you to set the color once and then over time modify that color independently over of the color over life module here. So if you were using initial color and wanted to drive it differently, you could do that way. Here, we're going to change this to a constant. Color over life always sets the value. It doesn't know about any other value that's been applied to the particle system. It overrides everything else. Whereas scale color takes whatever the color was and modifies it. So you can see it's already, because it defaulted to 0, it blacked out my particles. So now if I set this to 5, or 10 across the board, my particles get quite a bit brighter while maintaining whatever the color set here is. So if I go into my original color value and let's say make this a little more strongly red and get rid of some of the blue and green here, you can see my particles are now a lot glowier than they were before, and the more I amplify inside of the scale color over life, the more that will apply. If you want to do something where you allow the user or designer to set the color of the particle system, but you want to bias it towards a particular color, you could always, instead of setting the color like this with the color over life and then modifying it, if you do inside the color over life, change the distribution from constant curve, which is allows you to plot the value over time, to particle parameter. You can then drive, let's say it was something like team color, and I can now drive that color as a parameter and allow an end user to set it however he wants. But in that scale color, I can now say, well, as much as you're amplifying red, you're not going to amplify green and blue as much. So if I go into my color and set it to be 1 across the board, which would normally be white, you can see it's still pushing towards red because the scale color is only amplifying the red channel more than the other two channels. So this lets you kind of bias an effect towards a particular color range without taking away total control from the designer or effects artist, whoever's placing these or hooking them up instead of a blueprint, something like that. So now that we've got that going as a nice bright spark, we'll turn the GPU sprites back on, and now I have both effects going at once. Let's increase that. Bounds here, so now we've got a little bit of a bigger bounding box. It still doesn't want to. Yeah. So now we can do things like adding velocities. So initially, the particle is getting created. The GPU particles are getting created following these CPU sprites that are being thrown out. But they're not really doing much other than slowly losing velocity over time. If we turn the initial velocity back on, you can see it immediately adds that amount of velocity, so we start getting that kind of noisier look. But GPU particles allow us to use vector fields, which can do some pretty nice stuff. So I'm going to dock this here, and then go into my asset browser and allow myself to see the engine content so I can get to everything. And vector fields. I don't think we have any. Oh well, there's none in the starter content, so there's not a great way to show this off. So we'll talk about it a bit anyway. So a vector field is basically a three-dimensional shape, usually a cube, that is broken out into cells, and each cell has a velocity. So if you think of it as like a big Rubik's Cube, and each smaller cube inside the larger object tells the particle to go in a particular direction. So as you overlay them, or as the particles move from one cell in the field to another, they get pushed in different directions. So we'll add a little bit of acceleration to this so you can see them kind of coming off and making almost a digital wave here. So it looks like we've got a few questions. Why not use a sphere gradient instead of a sphere mask? The sphere gradient is a material function that essentially does exactly the same thing. I'm used to building from scratch. If I look up sphere gradient 2D and go inside of it, you can see it's actually doing essentially the same bit of math. It's just doing it in a way that requires a little more setup to do versus having this. This gives you more kind of parameterized controls, but for what I'm doing, this is working perfectly. What about a fog volume like UE3? Will that be coming to UE4 in the future? In the short term, not to my knowledge. Fog volumes in Unreal Engine 3 were done using features of the renderer that haven't been replicated in the same way for UE4, given that Unreal Engine 4 uses a very, very different renderer from 3. And it hasn't been something that our internal projects have driven a need for us as yet. I'm drawing a trajectory where my character is going to be launched to with multiple beam emitters. The performance is slowed down though, so is there a good way to draw a trajectory of particles, or is there a way to have one beam emitter do the whole thing precisely? So we did something like that for the Gears series for the grenade throws, where we would calculate the trajectory and then create a particle system that went through those points. So the trajectory was determined, and then the particles were created along that trajectory. Can you show how to inherit motion from a skinned character surface for the effect of a mud monster flicking blobs of mud around as it moves? So I can do something somewhat similar. So going back to my particle system here, I'll get rid of the basics here. That emitter location module that I used before has this inherit source velocity. And that basically means that whatever this module is doing, it looks at the parent and adds that velocity in. So we can also do that for skeletal verts and surfaces. So this particular module, given a skeletal mesh, will look at that particle's spawning surface and its velocity if you turn on inherit bone velocity. There are, I believe, let me switch projects here. So I'm switching over to content examples, and I'll show that a bit. Inside of the particle system, you define what bones you want to attach to. If that bone is moving, it then inherits that percentage of, there we go. So I'm going to open a level. So it inherits a percentage of that bone's movement. So you can throw things around. You can see effects. Looks like this content example may not have the effects. Yeah, there it is. So it'll take a second to load this as well. So when your bone is moving and you're spawning from that bone, if you turn on that option, it will inherit the velocity to a percentage. If you set it to 1 for x, y, and z, you'll have the exact same velocities for the particles that were coming from the bone. If you then add something like drag or an acceleration or something like that, your velocity will change after it's spawned based on those modules. You can also use negative values. So if you want a particle system to stream out in an opposite direction from the moving bone, you can do that as well. Might actually be in the skeletal. Ah, there we go. So if I change to simulate, you'll see this guy moving. So he's spawning these fire particles from his mesh, and some of those particles are inheriting a small amount of bone velocity, or will be in just a second. So if I change this to inherit bone velocity, turn these off so we can just see those. So there. Now, as he moves his arm, he's throwing those particles out much more energetically. If I change the if I turn off the inherent bone velocity, you can see now their location is updated, but their velocities are changed. And then if I do something like add some drag, you can see while they are inheriting, they don't go nearly as far because they run out of energy much more quickly because they're being dragged down. So that's a quick way to do that kind of flung mud. Now, if you're doing it with GPU particles, then you can do more collision-based stuff, though it won't accumulate. You'd have to write a system that says, I'm going to kind of throw out a blob and hit this point and do a decal, something like we've done with Jibs in Unreal Tournament, something like that. How would you make particles act like water? For example, a few water drops falling from a pipeline. If you do open the content examples, there's quite a few demonstrations of things like that, of having particle systems spawning from a location and either falling with velocity or colliding. There's also some examples in the Infiltrator demo that we released the content for a couple of weeks ago, showing how we did some of the drips and streams and stuff. There should be some content for that. Essentially what you would do is create a particle system here. So we've got PFX water drops, and if I wanted to have just occasional spawns, I could set the rate to be something small. And then give it a velocity with a little bit of an x vector. And then add some acceleration. So now I've got gravity causing the particles to kind of drift out. If I set the velocity alignment here, they're going to drip and fall. I could turn on collision and have them die when they collide with something. And now if I just drag this in the world, wrong button. So now, if you think of that as the end of the pipe, it's just dripping and hitting the surface. There's a lot of examples of things like particle events where you create a second particle system that has the splash effect that only gets spawned when a particle from a named system, in this case, I would do something like rename this drops, create a new particle sprite system that doesn't spawn anything. Inside the first, if you look under event, there's event generator. So I'm going to say this one will generate an event when the particle collides with a frequency of 1, meaning every time. And then in the receiving event, or the receiving particle system, this is generating an event when the particle collides. This is going to listen for that event, and we'll name it drop hit. In this receiver, we'll say if you hear drop hit, we're going to spawn 15 particles. So now you can see every time a drop hits, it spawns some number of particles behind. So you could do a falling droplet that splashes when it hits the ground pretty easily that way. We could do a small location module of sphere, get rid of -z so it only spawns up, change the radius to be pretty small, but use the velocity module, or the velocity option. So now it's going to move these particles away from the skin of the sphere, and we'll drag the acceleration over. So there, now we have a little bit of a splash when the particles hit. So can I give a quick demo of how to drive particle system parameters using blueprints? Can a particle emitter tweak material instance parameter values? Yes and no. I can give a demo of it and talk a bit about that. Particles can't actually drive the material properties in quite the same way that you would create a material instance and drive that. So let's say we're going to create a particle system PFX driven, and I'm going to say set the spawn rate to be a particle parameter and give it a name of spawn me. Change the parameter mode to direct. So instead of using the mapping function here where you say if you're given a value of this, translate it into that, we'll just do it direct. So we'll also change this to GPU particles so they'll be a little faster. So set the bounds. So now I'm spawning particles here with a rate of 10 because that's what's being driven here. If I create a blueprint and BP drive particles, I can find that particle system here, PFX driven, add it. So now I have my particle system as a part of my blueprint. And then let's add a variable of type float and call this spawn rate. Inside of my blueprint, I'll grab the variable for that particle effect and set a scalar or a float parameter. And I believe we called it spawn me. And then we're going to grab that spawn rate value and feed that in. So this is being done in the construction script. So this is before the game is played. This lets me set the defaults. So now if I go back into my viewport, I'm not spawning any particles at all. If I go and select my spawn rate, make it editable, give it a tooltip of defines the number of particles to spawn, and set the value to be something like 5. Anytime I put this particle system or this blueprint in the world, it will start off with the default spawn rate of 5, which is exposed here. It would help if I was looking at the right property sheet or the right detail panel. There. So here's the spawn rate of 5. If I set that to 50, my spawn rate gets a lot bigger. And of course, each blueprint can set a different value. So there's how to use a blueprint to drive a particle parameter. And you could do this for color, you could do this for lifetime, a number of different things. But inside of the particle effect, if I wanted to drive a material parameter, there's a couple of different ways and a few limitations in how we do this. So we'll just create a very simple M particle material. We're not going to mess around with any of the sphere mask or anything. We'll just do particle color into the emissive channel and opacity into here. So now this is going to be just a quad, and we'll set it to be unlit and translucent. So by default, what's going on when I use this particle system is the particle is pushing its current value, what it wants the color to be, into the material. That then shows up as some value on the particle itself when it renders. So we'll create that a new particle system, pfx param, and selecting my new particle material in all its gloried complexity. I'll set that. It'll recompile the shader. And when it's done, I have little white quads that are being spawned. Now, normally, particle systems are used to drive color. We define the color for flame or sparks or explosions or plasma, whatever. And then we use the opacity value to drive the visibility of the particle system. But there's a number of other ways you can use those same values or use another one. We have a thing called dynamic parameters. Now, I mentioned some limitations. Dynamic parameters don't work on GPU particles. So the way that you solve certain problems might be different whether you're doing it on CPU or GPU. Especially a lot of systems, you end up mixing the two. So you'll end up looking for solutions that will either adapt to both cases, or you'll end up with a material switch that lets you say, I'm going to use this behavior in one and not the other. So the dynamic parameter node has 4 outputs, similar to the particle color. They're slightly different in that you can name each one, so we'll just name them numerically. 1, 2, 3, 4. And then the default value is just 1 across the board. So say I wanted to have a fire turn into smoke or whatever. It really doesn't matter. We're just going to look for textures. So we'll find something that loads. All right, here's a caustics texture. We'll drop that in. And we'll say that it's going to turn into a fireball, because this is bound to be rather unpretty. So if we were doing something like multiplying the particle color by this explosion texture and making that the emissive color, compile it, and you can now see it's spitting out that fireball as basically opaque quads that fade out. And then if I do something in my color over life to say, make this excessively blue, my particles will get blue or purple or whatever over time. So there, I'm tinting that explosion effect because I'm driving its color independently of whatever the texture is. So that's an example of the particle color influencing how it looks. But what if I wanted to interpolate from my caustics texture to my explosion? So I just have a simple lerp from A to B. I can then use my dynamic parameter as essentially a material instance param, and then drive it this way. So right now it's set to 1. So if I preview this, you'll see it'll be the explosion texture. Perfect. Coming back into my particle, it's still that. But now if I put in my dynamic parameter node and refresh it, refreshing it tells it to check the material for the names of the parameters. If I just drop it in, it'll still work, but until I refresh it, it won't have the parameter names. So when I refresh, parameter names show up. If I put this on the curve editor, 1, 2, 3, 4. Now, each one of these channels can be defined, their behavior independently. So I'm going to change the type of parameter to constant curve for 1, and I'm going to remove these other curves here. You can already see it's now a blue caustic texture. So now we'll go from 0 to 1, from birth to death in this particle system, and we'll set the value to 1 near its death, and there you go. So now the particles are interpolating from a hideous blue caustic texture to a strangely purple, strangely purple explosion. So we'll set the color back to white, and it'll go back to being a little more normal. So again, not exactly what you do day to day in terms of the appearance, but having color and opacity driven separately from other values where you can interpolate between material properties. You could even do things like interpolating based on velocity. The dynamic parameter module, if you look at the value method, it can be used to output the velocity, XYZ, or the magnitude, which means it's moving in some direction at this amount. It doesn't look to see which vector it is, you're just looking for velocity. You could then interpolate between textures based on speed. So if you had a crisp version of the particle texture and then you had a blurred one because it's moving very quickly, you could do that and fake a little bit of motion blur into the particles, not just into the way the particle's moving in the scene. So you have a little bit of control there. One thing to note is because GPU particles don't use dynamic parameter, we end up doing that a little differently. So if you have, say, a particle system that say you're doing 2 teams CTF, you have red and blue teams. You might do something like this where you have red, blue being lerped. So this is setting your color, but you're actually using the red channel to do it. So now I can lerp between red and blue totally based on what I'm doing in my color over life. So if I hide my green and blue channels and set the value at there. So now I'm not setting this color inside the particle system. I'm setting the red channel's value and using that to influence what the material is doing. And this will work with GPU particle systems. So if you're doing something complex where you want to interpolate between something that you might need to do color plus texture plus something else, this allows you to kind of break out the color channels into discrete just data streams of I want the red to drive the particle color, I want the green to drive the opacity map, and I want the blue to drive the diffuse. All of that you can then break out and still use the alpha as an opacity or something else if you want. So this is a good way to look at the data that you're driving as not necessarily tied to being a color. It's just values. It's 4 different discrete constant values that you can drive independently. Can you talk about bounding boxes and explain how they should be used and why? So the bounds are the engine's assumption of where particles are going to exist in 3-dimensional space. If it can't see that shape, so if I go and turn on bounds, if I can't see that shape in my camera, and not the round one, but the actual cube, as I move that off screen, you'll notice that the sphere goes away because it's using the bounding box to determine the visibility of the system as a whole. And it looks at that to see if a particle system is behind you and the particles are unlikely to be shooting past the camera and become visible, we can just not render those particle systems, not use that for anything important. If I go in and set the fixed bounds, it looks at the current state of the particle system and decides that that must be the bounds of the system. If I then change this to GPU sprites, get rid of, you can see the dynamic parameter does not work with GPU particle systems. It still works exactly the same. As I can't see the particle bounds, the system no longer renders. So this is how we optimize for not rendering particles when they're not needed, by using the bounds to drive the visibility and therefore the rendering state of the particles. How to create a fire torch particle? Well, you can do it kind of like what I've done here, where you just have a number of colored sprites moving up and kind of changing color over time. If I go back into my particle material here, and let's say, see if we can find a sub-UV. So we have this concept, excuse me, of particle sub-UV, which means you have a single texture sheet that is broken out into essentially frames, and then it progresses from 1, 2, 3, 4, 5, 6, and then steps down and so on. And it does this by under the covers kind of scaling and moving the material around inside the quad that's defined for the particles. And setting that up inside of my material, we'll do particle sub-UV and multiply my particle color by this, and get rid of this color offsetting we were doing. And then inside of the particle properties, we'll change this to linear blend and 6 and 6. We're also going to use this as the particle opacity so that it's not quads. There. So now I have particles that are all starting in the first frame of that particle animation, the very source one there. And then the next thing we're going to do is do sub-image index. And this is the curve through which it will animate the particle system. So I have, 6 by 6, 36 particles. It's 0, 1, 2, 3, 4, 5, and so on. So it's 0 through 35. So the end will be value of 35.01. And this will basically say I'm going to animate through all of these values, and at my death, I'm going to be almost completely back to, or I'll be slightly past the end particle. And that just gives you the complete animation loop. If I were to do, move this to 0.25, you can see the whole particle system plays through those frames really, really quickly, and then it freezes on the last frame for the rest of its life. So from birth to death, we'll go from 0 to 1 minus the total number of frames plus 0.01 to just squeak it past that end frame, and all the interpolations will work nicely. So back in the color over life, we will do something with a little more appropriate color, because this is an RGB flame. So we'll set the color to be white. Now we've got a white flame. And let's set the color here to be a really dark red. And we'll set the color at the beginning to be a really hot yellow-orange. So there we go. I'll get rid of the bounds so you can see it. And if I cut the lifetime back a bit, so I can get a bit of a torch flame going right there. And just like I did before, I'll use scale color over life to drive my kind of overall brightness. So if I want that kind of glowing torch flame, there. So now I've got much more of a kind of hot flame. Could you use particles, GPU or otherwise, to change the blending of a material where the particles collide with the ground or fake the accumulation of snow? Unfortunately, there's not a very good way of doing that. The particle systems, to keep them efficient, don't do a lot in terms of writing to the world around them. You would be better off writing a class that explicitly did something, essentially dropping decals where they landed. And there have been teams that have done things like that. You'd probably want to use CPU particle systems, and on their collision event, create a decal at that location, and then have a manager that says no more than X number of decals, and the oldest one needs to go away, and the new, so that a newer one can be completed. How can you spawn more particles without sacrificing performance, CPU or GPU particles? So with CPU particles, they are more expensive per particle to have, but you have more influence over them. You can do things like dynamic parameters. You have more kind of per particle interaction in terms of setting the collision type and how they're going to react when they hit things, rather than just die or bounce. You can control the number and things like that. Whereas GPU particles are much more efficiently spawned, but they're much more fire and forget, where you spawn the particle, it does its thing, and you have no real control over it other than setting some properties over its lifetime that are predefined. So GPU particles allow you to spawn a very large number of them, while CPU particles give you the kind of intensive control that you might need to accomplish some effects. The spark that spawns trails is a good example. You can control the spark's momentum and behavior and how it bounces, and have a few of them, but then fill the effect with GPU particles to get a more a fuller, more rich result. How do those near mirror reflections work efficiently? Are they produced by a single cube map that's rendered each frame, or what? So we have what are called reflection capture sources that are scattered throughout the world. They look like this, and they basically capture a cube map for their location and blend them together. So if I go and look at reflections, you can see the reason you can see kind of repetitive shapes is because all of the cube maps are capturing something similar but offset by their location, and then those are being blended together based on the camera's position in space. So as I get closer or further away, the blends will change to produce a approximate reflection result for an environment. On top of that, we layer in our screen space reflection. So when you're looking at the scene, we're looking at the results of that buffer and using that to approximate real-time reflections. So if I look at reflections again and select all of my reflection capture sources, all that you're seeing now, all the reflections on the ground from the particles and things like that, that's all coming from the screen space reflection. So the only it's being layered in and added on top of the reflection captures so that we get dynamic things like particle systems, characters, moving objects showing up in the reflection results, but we aren't spending a massive amount of computation time to figure out what those reflections are going to be per frame. Whoop. No. Knocked over my mouse, lost my mic. I'm going to do it again. There we go. So how would I go about making a dry ice system where the particles spill out from the emitter and then spread out over ground, like dry ice in a coffee mug? So for Something like a small effect that you'd probably use GPU particles. You could even use CPU particles with a few GPUs behind it. For larger effects, you want to be careful because, like, if you're doing a cauldron in the middle of a large playable space where you're walking through it, your bigger problem is going to be the number of particles to pull that off means your um, overdraw is going to get progressively worse the more particles you add. But in terms of just doing kind of the simple one, I would say something like, so we will do our extremely simple particle system again. And we'll do the whole sphere mask bit. So building up pretty much exactly the same thing I had before. 0.5 for the two location, the comparison and the radius, and then a hardness of 0. Oops. Use that as the multiply against my opacity, and pseudo smoke dot. So now we're spawning this particles. So the first thing I would do is define a cylinder. So this would be the size of your object, whether it's a coffee cup or cauldron. And I'm spawning from a cylinder in space. So I've changed that to have a 0 height, so now it's just a disk. I'm going to change the size of the particles to 10. They're all going up to begin with. If I let them go up a little ways and then give them a little bit of velocity along the cylinder by using that velocity value again, and then add a little bit of acceleration, along down. So now I'm basically having bubbles slowly come up and out. If I drop this acceleration down, we'll end up with not quite so vigorous a system. And if I change the cylinder to be surface only, they'll only spawn from the outer edges. So now, just to see what this looks like so far, we'll drop it in the world. So there's particle smoke gently coming out and not colliding yet. So we'll add collision, and we'll say it'll kill the smoke on collision, but we are going to allow between 3 and 6 collisions. So now those particles are going to hit and kind of settle. And we're going to change the damping factor. So now with a damping factor of 1, it's how much energy is being returned. So the amount of bounce. So we're going to actually allow for a little bit of lateral motion, but no vertical. So now the particles will hit and slide out a bit. So if we increase the outward value a little bit more, they'll hit and slide out. Better if I wasn't on a white floor in a white room, but you could also then have size change over time. And I'm going to lock all 3 axes because I don't care about any of the individual ones in particular. And we'll say that this will get larger by that much. And we'll up the initial size a little bit. And just so we can see it, I'm going to change the color to black. Because this is a translucent system, this should work just fine. We'll just end up with a particle system we can't actually see all that well in the preview window, but will show up much better here. So you can see they hit and slide out a bit. If I increase the number of times they are allowed to collide, they'll go further because they won't die off as quickly. And if we add a little bit more of their value back, they won't hit the ground and basically slide along it with no restitution. And then we can say the lifetime of the particles vary a bit, so they can come out and kind of float away. But this isn't the kind of thing you would want to do on a large scale, because in shader complexity mode we can see the more particles that we spawn and the more of them that overlap in a single space on the screen, the more expensive it gets. Something like this particle system you'd want to be very careful with, because if your player is standing here all the time, you're going to consume a lot of your frame buffer's performance rendering that fire. But if it's something like my little smoke thing where it's just sitting on a table bubbling away, it's not likely to take a whole lot of performance away from the rest of the scene. So for weapon, bullet, particles, and trails, would I use this particle system? We certainly do. There's a couple of different ways to do something like a bullet trail where I shoot and you see a stream behind it. One is to spawn the particle system completely independently of the bullet. The bullet hits the location and then you spawn something that zips in that general direction, which can look great for cinematics, but not always what you want for gameplay, because a lot of people look at the bullet trail as being an indicator of where the person was aiming. What we've done for things like gears is we use beams. So we spawn a beam from the muzzle of the weapon to wherever the bullet hit, and then we pan very rapidly an effect down that trail. So the beam is blank and then has essentially the bullet shape off screen on the beam's mesh, and we zip it down the length of the beam over a very short period of time, and that gives the impression that the particle system is traveling with the bullet, when in fact the bullet's already hit. We're just doing this extremely rapid effect. How would you create a huge weather system using clouds without running into performance problems? You will, depending on how aggressively you LOD things is where you're going to run into your biggest performance savings. Obviously, if you have a large number of particles overlapping, you will just cost yourself performance. It's essentially inevitable. I mean, if you have a cloud that's made up of a ton of sprites and you go up to it, then you're going to consume some performance with that. However, what we do a lot is have different LOD levels within a particle system driven by distance. So when I'm far away from something, it's a few particles. When I get close, it's a lot more. And then we also do things where we use complete proxies. At a far distance, the blueprint can swap out a card for a particle system or something like that. So for doing just a cloudy sky where you can fly through it, you want to carefully kind of manage your detail based on your distance to a surface, so that you're not constantly rendering huge layered clouds that cost you this kind of shader complexity performance. So this is definitely something that you would want to have, maybe that big on a screen, taking up, a bit of the screen, but not filling the screen to this degree where every additional thing on your screen is already has this additive performance cost to it. How would you go about making small clouds when you fall from the sky and you move through them? You have to see these clouds in the distance. This would be something similar where you have a say, cloud mesh that looks like a cloud, and then as you get close to it, you replace that cloud mesh, whether it's a quad or crossing sheets or a volumetric, or not volumetric, but a sphere or something like that that maybe you displace with vertex shader, and then you just kind of interpolate into this particle system. So the last thing I'm going to answer is, how would you make it rain across the whole map without taking a huge performance drop? So there are a couple of different things that go into that. One is attaching the particle system to the player and then only activating it when the player is near somewhere where it's supposed to rain, so that you're not costing performance. If the player is inside, the particles aren't colliding with stuff to block them. Another part of that is having a couple of different particle systems. One that is near the player, that moves with him, that is the majority of the rain. It's what gives the look of being in a rainy environment. And then having another particle system or two that are placed in the scene that give specific, like if you want to see rain hitting something because it's an important thing, like a wrecked car or something, you might have a particle system on that that gives the look of rain splashes on that object. We also do things like having downspouts are specific particle systems where when the particle collides, it does the splash. So as you move through it and it hits your body, or if something else is moving through it, or even if it's just hitting the ground, it looks like part of the scene, and it gives you that effect. So the only way to do a really good worldwide or level-wide rain system, in my opinion, is by kind of carefully putting one around the player that looks like it fills the space when it actually only fills, say, the first 30 feet around the player. And then you have other things like material effects that look like it's raining, or other particle systems that kind of fill in the distance but don't spawn nearly as many and don't cost your performance budget. Using GPU particle systems goes a long way for that, because you can spawn a lot of them that are very, very simple without nearly as much performance overhead as our CPU systems currently have, especially if you're wanting to have a large number. GPU particle systems allow us to spawn up to 1 million is the current limit. Obviously, the closer you get to that limit, the more performance you're consuming. It can do that many. You just wouldn't want to do that all the time. But a few thousand or even 10,000 in a system where you're not doing a whole lot of other things, and the particles aren't very large, so they don't do the whole overlap and cost you tons of performance like the smoke clouds that we were looking at before. That's a very reasonable thing to do, especially for something like rain. So that was my talk. I hope people found it at least somewhat interesting and entertaining, and I'm sure I'll be doing another one of these at some point in the future. And I hope everyone has a really great day. Thanks a lot.